Imagine a train with no exhaust, no steam, no diesel smoke, no sound of pistons or cylinders working against compression, just motion. A vehicle moving through a sealed tube at speeds that conventional railway engineering said were physically impossible, not because of power, not because of track, but because of air. Because the moment a vehicle accelerates beyond a certain threshold, the atmosphere itself becomes the enemy. Drag, pressure accumulation, the entire mass of air ahead of the vehicle, refusing to move fast enough to let it through. Every railway engineer who ever pushed a locomotive to its structural limit understood this. The gradient was one constraint, adhesion was another. But air, invisible, ambient, everywhere, was the constraint that no locomotive wheel arrangement and no boiler pressure could solve. In 1945, a man named Robert Goddard believed he had solved it. He was not a railway engineer. He was a rocket scientist, and the solution he designed, formally filed as United States patent, 2,511,979 on the 21st of May, 1945, was a railway system that operated inside a vacuum. No air, no drag, no aerodynamic limit. The design was called the Vacuum Tube Transportation System. Nobody built it. Nobody, for 70 years, could afford to. That is the beginning of this story. Before we continue, if this kind of railway history matters to you, consider subscribing to the channel. Every video here is built around the locomotives and railway systems that the standard histories overlooked, the machines that outperformed their celebrated counterparts, the engineering decisions that were ahead of their time, and the railway lines that shaped nations without receiving the recognition they deserved. If that is the kind of documentary worth watching to you, the subscribe button is how you tell us. And we want to hear from you. Did you work on the railways as a driver, a fireman, a fitter, a signalman, a track engineer? Did a parent or grandparent spend their career on a railway that is no longer operating, on a locomotive class that is no longer preserved, or in a workshop that is no longer standing? Leave it in the comments. The people who actually operated these machines know things that do not appear in any published railway history. We want to hear from them. Now, back to Robert Goddard and the patent he filed 7 weeks before the end of the Second World War. Robert Goddard is remembered for rockets, the liquid-fueled rocket that he launched in 1926, the work that made NASA's existence decades later, break-time MX-05s, possible. What is not remembered, what appears in almost no engineering survey of railway history, is that Goddard also designed a railway system. Break-time 05s, not a metaphor, not a theoretical sketch, a detailed break-time equals 05s Tati formally patented engineering proposal for a vehicle that would travel inside a sealed tube from which the air had been removed. Break-time 05s. The principle was straightforward. Aerodynamic drag increases as the square of velocity. Double the speed, quadruple the drag, triple it. Brake times 05s, 9 times the drag. For any vehicle moving through air, speed is eventually bounded not by the power of the engine, brake time 05s, but by the energy cost of pushing through the medium itself. Remove the medium, remove the drag. A brake time 05s, a vehicle inside a vacuum tube faces no aerodynamic resistance. Brake times 05s. The only forces to overcome are those of magnetic levitation and the linear electromagnetic propulsion system, both of which, in Goddard's design, brake time 05s, were electrically powered and theoretically highly efficient. Brake time 05s, the system he described in patent 5,511,009 in 79, used electromagnetic coils to both levitate the vehicle and propel it forward. The tube was sealed. Brake time 05s, the air was evacuated. The vehicle had no wheels in the conventional sense, no axles, no flange contact, no rolling resistance in railway terms. Brake time 05s. The adhesion problem was eliminated entirely. The tractive effort was not a function of adhesive weight. It was a function of the electromagnetic field. The engineering was sound. The problem was the vacuum. The vacuum was the problem. On Earth, atmospheric pressure at sea level measures approximately 101,000 pascals. To operate Goddard's system, that pressure had to be reduced to near zero and kept there continuously across every meter of tube for the entire operational life of the system, every seal, every joint, every access point, every station. Any leak anywhere in the tube was not a maintenance inconvenience. It was a catastrophic failure. The vacuum would equalize. The vehicle would decelerate into a column of air it had no mechanism to push through. The infrastructure cost of maintaining a near-perfect vacuum across a railway network of any practical length was, in every economic analysis conducted through the mid-20th century, prohibitive. Railway companies were not going to build it. Governments were not going to fund it. The engineering was not in question. The economics were. Goddard died in 1945, the same year the patent was filed. His wife, Esther, saw it granted posthumously in 1950, and then for most of the following decades it sat. The design that required a vacuum had no planet on which a vacuum was economically available, until engineers began to look at Mars. Mars has an atmosphere, but it is not like Earth's. The surface pressure on Mars measures approximately 600 pascals, less than 1% of the atmospheric pressure at sea level on Earth. Not a hard vacuum, but close enough in engineering terms to change the calculation entirely. On Earth, building a vacuum tube railway means constructing sealed infrastructure and then spending continuous energy removing the air. The atmosphere is the adversary. The pump runs forever. On Mars, the atmosphere is already almost gone. The tube does not need to be pumped down to near vacuum. It is already at near vacuum. You would only need to seal it. To maintain the internal pressure at a level that allows the electromagnetic propulsion and levitation systems to function. In 2015, NASA engineers and space systems researchers examining the feasibility of Mars surface transportation identified this reversal. The Hyperloop concept, the direct descendant of Goddard's 1945 patent, developed and refined in the years following his death, had been dismissed as economically unviable on Earth in part because of the vacuum infrastructure cost. On Mars, that cost was negligible. Additionally, Mars' gravity is approximately 38% of Earth's. The energy required to propel a levitated vehicle along a flat electromagnetic guideway on Mars is a fraction of what the same system would require on Earth. The design that no terrestrial railway operator could afford had, 70 years after it was filed, found the operating environment it was always suited for. Robert Goddard filed a patent for a railway system in May 1945. He died 3 months later, before the document was processed, before anyone understood what it would one day mean. For decades, the design sat in the patent record alongside thousands of other proposals that were technically coherent, but economically impossible. The history books that covered Goddard covered the rockets. The railway system was not mentioned. In 2015, the engineering community returned to the question of how humans might move across the surface of another planet. The answer they kept arriving at was the same system Goddard had described. Not because anyone had rediscovered his specific patent, but because the physics of a low-pressure environment points in only one direction: vacuum tube, electromagnetic propulsion, no aerodynamic drag, low gravity reducing propulsion energy still further. Goddard's design was not ahead of its time, it was ahead of its planet. The railway that Earth rejected may be the railway that Mars requires. The engineering record does not change. The environment that makes it possible was 225 million kilometers away. That is what the standard histories did not record. That is what this channel is for. If this is the kind of railway history you want to keep watching, subscribe to the channel. There are more locomotives, more railway systems, and more engineering achievements still to document. And if you have a connection to what you just watched, a family member who worked in aerospace engineering, in vacuum systems research, or in the railway and transport industries that this design was proposed to transform, tell us in the comments, what did they work on, which laboratory, which railway, which engineering department. The people who understood these systems are not in the standard histories. But the engineering record depends on what they remember. We want to hear from them.